Again, I'll say a little bit.
Is it not a show?
Is this a cruel joke?
Wiring you for some.
Yeah, I don't think we need all this. Could you turn this off?
Hey, you have to talk up loud.
Or, well, this one's on, so you see that's why that one is, it's been made redundant. As I said, this is going to be more of a chemical talk, and in 20 minutes, it's hard to give all of the sort of history behind the additives or the engine oil, lubricant oil side, lubrication side, but I'm very happy that Norm asked me to do this. Thank you, Norm, to represent lubrication and lubricant additives. And I'm happy the Lubrizol Corporation also is letting me do this as well for them as well as the rest of the industry. We're going to move downstream several miles from where we started here with cat cracking and some of the previous speakers. And I'm going to talk about, just give you a bit of overview of additive chemistry. Talk a little bit about, I'd like to focus in on dispersants and detergent chemistries for reasons that I'll make clear in a minute. And I'm much more interested in the future than the past. And so I'd like to talk a little bit more about what's happening and what new technologies are coming along in this area as well. Let's first look at from an oil company perspective, is what is an engine oil. Besides the base oil, the biggest portion of an engine oil is really the performance package. Makes up to about 20% of a lubricant, of a final lubricant blend. Viscosity, monocoil, 4-point depressants make up a smaller percentage, but it's that a performance package that I'd like to concentrate on. From a lubricant company additive perspective, the detergent and dispersant really make up the lion's share of that package. If we're now looking at just that 5 to 20% that was on the previous slide and this slide. So really the chemistry of the dispersants and the detergents really do dictate a lot of the properties of the lubricant. And again, you know, I'm choosing to give a few perspectives on some chemistry behind additives that really dominate a lot of the chemistry that's in the oils. And so I'm going to talk more about the dispersants and detergents than anything else. I want to give an overview of detergents, but in view of the time, I'm going to talk about these in the context of the next slide. And Jody Kochis is in the back here. You can correct me if I'm, who's a detergent chemist. So you can correct me if I'm saying any heresy up here, because I'm more on the dispersant side. But detergents actually, if you look at what they are, they're composed of both a surfactant base, which is represented by the surfactant head and tail molecules there, which solubilize a core of basic materials, in this case some calcium carbonate. And one of the discoveries which was made serendipitously was that one can take a alkaline earth or alkali base hydroxide and blow in CO2 and form and this is a process known as overbasing. This forms in this case, starting with the calcium or a lime base, one makes a calcium carbonate core, which is solubilized by the micelles shown here. And so what has developed historically, what has developed over in the industry is what we call overbase detergents, which are basically, no pun intended, base capacity, which is available to neutralize deposit and corrosion forming acids which form an internal combustion engine. And this is a schematic of what that looks like. speaking of nanoparticles, which are have a lot of getting a lot of attention these days. These particles that are of calcium carbonate there are on the nanoscale. They're about in the 20 to 30 nanometer size, and so nanotechnology's been in the lubricant industry for many years, much before the current interest in these structures. The second structure here is meant to show that the surfactant themselves can also form protective layers on the metal. And so the idea here is that these two components, namely the over-base component and the surfactant component, really work together in synergy, do things like inhibit rust and corrosion, because the basic core neutralizes these precursors of these materials, and as well can form these protective layers on metal surfaces. They inhibit oil degradation by similar types of mechanisms, and besides solubilizing the base, they can also solubilize polars, including metals and metals which can catalyze corrosion, combustion, breakdown of the degradation of the oil. They also reduce high temperature deposits by similar mechanism. As I said, they solubilize polar components. This is a famous slide, and probably one that can be duplicated by many of our competitors in the industry, in which shows that it's pretty well known that the base number, or the total base number, TBN, shown here by the solid lines, decreases with usage of an oil, and that the acid number increases. And again, these can be correlated with precursors to deposits and corrosion and bad things that happen to an engine when you let the acid number get too far out of hand. And these equivalence points, high and low, shown here by the purple and pink arrows, are really where, again, it's been shown by many correlations that this is sort of the point at which one considers the oil to be used up, or the base capacity is at such a point where degradation and of engine parts will start to occur. Things like this, shown on the left, is some varnishes and deposits which form on pistons if this process is left unchecked. And it's believed that many of these deposits are formed by these carbon acids, particularly carboxy nitrates, which form the precursors to these types of varnishes. And of course, on the right is an acceptable piston, which is within that range of base capacity. Moving on to dispersants. Again, I'm going to pass this one in the interest of time and go right to the schematic. Dispersants are similar in general structure to detergents, except that the tail is longer and it's a different polar head. Generally, what works well in dispersants is a longer hydrocarbon tail and an amine head. By the mechanism shown here, these suspend soot and wear particles, particularly metals, in an engine as with use. The soot particles is particularly a bad actor and becomes important, particularly in diesel engines. And again, if left unchecked, this can create great increases in viscosity and wear, because the soot particles can get too big. Again, these particles here are around the hundreds of nanometers when they're properly dispersed. And again, that's what this chemistry is designed to do. Shown here are some real micrographs of, if you look at a one-fold dispersant level, and these are now the soot particles, which in one of our engine tests, you can see that the average size here is about 1360 nanometers. As one adds dispersant, those particles not only get smaller in the average size, now about 460 meters as you roughly double the dispersant concentration, but you can also see that they're less dense as well. And when we get up to a 5-fold increase in the dispersant level, the particle size, average particle size, is down to about 200 nanometers. And this last picture is really what one would consider to be an acceptable level of dispersed carbon, which will not really do any damage to an engine, whereas the other two, particularly the first one, would definitely be the source of wear particles. Again, I want to get into some chemistry now in the interest of time. Let me just talk about what, again, historically has developed in the industry. What we really have in these additives are an oil-soluble backbone connected to a polar end group by what we call a hook. For the detergents, the dominant chemistries are typically a C16, but they can be anywhere really from a C12 to C32 linear or branched hydrocarbon backbone. The hook is usually an aromatic group, usually a sulfonate, phenate, or a salicylate, and the polar end group is simply the corresponding salt, usually calcium, magnesium, or sodium. For the dispersants, it has a longer backbone, as I said, which is dominated by the polyisobutylene chemistry, a molecular weight range about 500 to 2,000. Maleic anhydride is the predominant hook, although there's also some phenol formaldehyde chemistry based on mannate chemistry. And again, the polyamines are generally the polar end group. Now, these have been really refined over the years, and when you go into your Target or Walmart or whatever and see that or Murray's or whatever they have around here in the Chicago area or wherever you come from, when you see that you pay $1.19 or 99 cents for your quart of oil, whereas you want to go buy a bottle of water, it's over $1. The reason that these things are so cheap is because over really particularly the last 50 years, these things have been really refined to get the best chemistry for the cheapest cost. And that's particularly true of the hook and the polar group. It's really difficult to compete with maleic anhydride or some of these detergent alkylates and the polyamines in the case of the detergent. So really the sources of improvement here have been more attention on the oil-soluble backbone, which gives much of the properties, because much of the bulk of these materials is the backbone. So I'd like to talk just briefly about the currently available backbones and where things might be going from here. Conventional polyisobutylene obtained from places like Lubrizol as well as BP makes these. There's what's called a high vanillidene PIB, and I'll explain that a little bit later. Actually, fairly quickly, Norm, because we're going to be ending here pretty soon. And then there's some other down the road olefin copolymers and polyalpha olefins that Mitsui and ExxonMobil makes. Just to give you some background into one of the things that was really I think a kind of a landmark in the industry was recognition that polyisobutylene could be catalyzed by aluminum chloride, and that the end group you get is not what you'd expect, but it's basically a 5-carbon end group that has both the cis and the trans arrangements, as well as this is showing the tri-substituted isomer and the tetra-substituted isomer, which are the predominant end groupings here. But this is a very different end group that one would expect, and this is what the so-called high vanillidene polyisobutylene basically gives you the end group that you would that a freshman organic chemist would draw if you asked him what is polyisobutylene. So it became very important in the industry that a way to process these in different ways became discovered. And in fact, the conventional polyisobutylene is really the predominant player because it's the cheapest. These other less known, but maybe more known in the future, are more similar to the high vanillidene polyisobutylene in terms of the end groupings. But just to give you the basic chemistry here, The conventional polyisobutylene really lends itself to a Diels-Alder reaction. If you can see here, there's a dying structure that can form, and that dying structure it can be very reactive with isobutylene, and this lends itself very well to processing by chlorine dehydrochlorination. Again, this was one of the major discoveries in the industry, and one that I think predominates still today, that one can process these types of polymers by this route. The high vanillidine and the polyalpha olefins and olefin copolymers cannot form these types of dying structures, and so they have to be processed by what is shown here as a thermal ene reaction. And again, as I said, this is a slower reaction, one that requires heat, but does not require chlorine. And again, these are the two major paths by which backbones used in the additives that go into your engine oils are made, and can be done very cheaply in the industry now. The alkyl phenol is just a straightforward, and that gives rise to many of the manic type intermediates. I guess in the interest of time, I'm going to move forward here a little bit just to get to the end of this, and if you don't mind me just going through this. This is some of the things that we'd like to get from olefin backbones, and we can go through that list later. But I think maybe what I'll do is zip forward here, if I can do so. Just to say a little bit about the future. As I said, these systems chemically have been really modified and tailored, and we're talking about extending life, improving the durability of getting longer drains in oil intervals, making these things even cheaper, making these things compatible, and the components compatible with catalyst systems. Elements like phosphorus and sulfur, which I didn't talk about, but are in many of the other additives, particularly the anti-wear additives, are important, and also being accountable for these things from cradle to grave. So I think what the industry is, and what particularly at Lubrizol we recognize, is that we're asking things of chemistry that maybe chemistry needs some help with some other systems, and by that I mean the types of performance systems which combine chemical, mechanical, and electronic components, and targets our markets in a new way, where we need to extend service and reliability, reduce cost even further, and create convenience. And examples of this, I have just a couple here to show in terms of advanced fluid technology, transportation systems, and use of emulsified fuels. The advanced fluid technology, again, I'll just go quickly, but this is just recognizing that there's a lot of variations. Usually the joke we have in the industry is that if you formulate something to try to fix one problem and add something to do it, you usually create another problem. For example, here's for thermal stability, soot control, seal compatibility, and this bottom one is really sludge performance. Here's a typical high base, high TBN formulation to do this, and you see it's not the greatest on seal compatibility. You can fix that by making reducing the TBN, but then you screw up the other things that you're trying to do. And through a better understanding of these types of interactions between the additives and with the base oil, we're able to do things like this. And this is an actual formulation that was computer generated from a lot of the data that we have at Lubrizol, and I'm sure there are many analogous systems that are looking at smart ways to do formulations where we're able to put our system together that basically addresses all the problems. Another thrust for us is a venture between Lubrizol and GD Transportation Systems, in which we're looking at diagnostics combined with onboard dosing and troubleshooting systems on board a locomotive, and we now have a number of these systems on board which look at and diagnose and fix problems with crankcase and compression oil, and also it has an onboard oil change. traction motor gear replacement, diagnostic monitoring of fuel and coolants, and there's also a neural network communication, which not only tells where all these locomotives are through a GPS system, but also monitors the condition of the fluid and troubleshoots any operation on board. So there's chemistry involved here, but we're trying to make it work harder by adding to it a lot of these performance systems. One last example, which was talked about a little bit before. Well, ethanol is a bad fuel, but water is even worse. We don't want it to be a fuel here. What we do is a product called Purinox, where we're mixing, creating a stable emulsion of what is through an additive package with water, which is in this case 20% water, 80% diesel fuel, and other seasonal components that are blended in a unit, which gives this what looks like a milky diesel fuel. And this is being used both in on-road and off-road applications. And by simply changing over to a Purinox fuel, you can reduce both NOx and particulates by an average of between 20 and 30%. And this is being used both in North America and throughout Europe, both for on and off-road applications. And it's been very successful, particularly where there's been large capital investments in equipment, and simply by changing the fuel, which is more expensive, obviously, on a BTU basis, because you're replacing the fuel with BTU units with water. The basis for this working is that it creates a different temperature profile and lowers the temperature during which, at the right crank angles at which I'm playing here, at which NOx and soot particles are formed during the combustion cycle. So again, examples where the types of additive chemistries that we're looking at here are getting into additives for fuels, and one of the big thrusts that this will have an effect in where we need to put these things to work is in the environment and the emissions areas. So that's, you can pretty much hear what I've said, and those are some of the people. Again, John Podolsky is a dispersants manager, Jim Roski is detergents, and the rest of the people have various roles in helping me put this together. And we have kind of standard talks around Lubrizol that we pull off of the net. So I pulled a few together, and hope gave you a little perspective on where the industry is, where we're going, and thank you for your attention.
Hi, Jim. I understand.